Hello, my name is Sam, and in this series we will learn how to simulate molecular water on a computer. In order for the computer to understand us, we will use a programming language. The language that we will use is Julia, since it's fast and not too difficult to code due to its dynamic typing capabilities. Another great thing about Julia is that you can use it in Jupyter notebooks. To make our simulations run fast, we will delegate some of our computational load to the graphics card using the CUDA platform. In this schematic, it is shown how we will send the short-range interactions to the CPU while we calculate the long-range interactions on the GPU. For the GPU, I use an NVIDIA RTX 2060, but really any NVIDIA GPU will do, as long as it supports CUDA. For the visualization of our simulations, we will use Blender. We will use this because it's a fantastic 3D program that is also free to use. Okay, so now that the general idea of what we're going to do is in place, let's think a little bit about what we are going to simulate. Water. What is water? Let's have a closer look at the water molecule. It consists of two hydrogen atoms bonded to an oxygen atom. The distance between the oxygen and the hydrogen atoms is 1 angstrom, and the hydrogen-oxygen-hydrogen angle is 104.5 degrees. In our simulations, two kinds of movement will be allowed in the water molecule. The first one is bond stretching and concerns the movement of the hydrogen atoms along the bonds. This movement is described by a harmonic potential. The second movement is angle bending, and it involves the variation of the hydrogen-oxygen-hydrogen angle. This movement can also be captured by a harmonic potential. Now we will consider the intermolecular interactions by considering two water molecules. We will allow for two potentials that only operate between different molecules, the Coulomb interaction and the Lennard-Jones interaction. Let's start with the Coulomb interaction. The hydrogen atoms are positively charged, while the oxygen atoms have a negative charge. The Coulomb interaction mediates the force between these charges, as opposite charges attract and similar charges repel. For example, this force causes the hydrogen and the oxygen atoms to attract. The Lennard-Jones potential, on the other hand, takes into account the van der Waals force, which is attractive. When the molecules become too close, the Lennard-Jones potential causes the molecules to repel, which represents the Pauli repulsion. For simulating the molecular water, we will follow the scheme of molecular dynamic simulations. This involves 3 steps. The first one is to define the interactions between atoms through the energies. The second one is to calculate the forces on the particles through those energies. And finally, we integrate the equation of motion through the forces. In this series, we will work our way backwards. And therefore, in the next episode, we will start with programming the integration of the equations of motion using the Verlet velocity integration method. See ya!